right, in this lecture we want to review active filters. In this lecture we'll talk about active low pass, high pass, band pass, and band reject filters. Now the active filters that we'll go over in this course are all constructed using an op-amp. So here is the traditional or conventional inverting op-amp circuit. You notice that your input voltage is connected to the inverting terminal. The non-inverting input is grounded, and then the output is left open. There is an input impedance connected to the inverting input, and then there is a feedback impedance that connects the output back to the input. If you remember anything about your op-amps, you know that the output voltage in the circuit is equal to the ratio of the feedback impedance to the input impedance. You may have seen this in circuits 1 as resistors, not impedances, but it's pretty much the same principle, same kind of circuits, just we're dealing with Z instead of R. So your transfer function then would be minus ZF over Z input, or the impedance in the feedback loop over the impedance in the input branch. So if we want to construct a low-pass filter using this kind of circuit, we basically put a parallel combination of resistor and capacitor in the feedback branch, and then we put an input resistor into the inverting input on the amplifier. So using our relationship for the transfer function, that H of S is minus Z feedback over Z input, we take in the feedback impedance the parallel combination of R2 and 1 over SC, and the input impedance would be R1. So then we come up with an expression where some algebra was obviously done here, and K, which is going to be defined as the gain, is basically R2 over R1, and omega C, which is clearly from the looking at the denominator of the transfer function, is going to be the cutoff frequency, is 1 over R2C. So important to realize that the resistor value that determines the cutoff frequency is the resistor R2. And so if a person wishes to have a gain greater than 1, then it's R1 that should be adjusted to achieve the gain K, not R2, because R2 is going to determine the cutoff frequency. So that's an important design consideration. If you, for example, are specified a given capacitance and asked to design a filter with certain specifications, you would first select your R2 based upon what your design cutoff frequency is. Remember also, frequencies have to be in radians per second in order to use these equations. So if your design specifications are in hertz, you'll have to convert that first to radians per second. Then once you have achieved your cutoff frequency specification, you can meet any gain specification by adjusting the ratio R1 over R2 over R1. Also remember that this is not in units of dB, it's strictly in units of ratio. So if your specification is given in dB, then you would have to figure out, basically that would be 20 times the log of K. So you have to back calculate to figure out what K should be for your particular design. So this is the Bode plot of a low-pass filter where you have a gain of 1, and you can come in and read roughly at the 3 dB down point that in this example the cutoff frequency was set equal to 1. This is also known as a prototype filter, which we'll discuss later. So anyway, that is your Bode plot of a low-pass filter. A high-pass filter has a slightly different circuit configuration. Connected to the inverting input would be a resistor in series with a capacitor within a single resistor in the feedback loop. We can write the expression for the transfer function using the general feedback over input impedance ratio. Doing some algebra, we come up with, once again, a gain factor K, and then we have S over S plus omega C, which you probably recognize from our discussions on Bode plots as being the conventional type of function that would represent a first order high pass filter. Once again, K then is going to be the resistor ratio, feedback to input. In this case, for the high pass filter, it is the input resistor that's going to determine the cutoff frequency. So once again, you would design your circuit by choosing R1C to satisfy your cutoff specification, and then you can select R2 to meet your gain specification. And remembering, in this case, that gain would not be a DC gain, it would actually be the gain in the passband or the high frequency part of the spectrum. And also remember, these active filters, they can have a passband gain of greater than 1, which is part of what makes them advantageous over passive filters. Once again, here is a Bode plot. In this Bode plot, you're actually, in the example in the book, you're actually given this Bode plot and asked to design a filter that will give you this Bode plot output. So first thing we have to do is we have to look and verify that indeed we do have a slope here of 20 dB per decade. So if we kind of estimate here from, say, if we go from minus 20 to 0, then we do see that that occurs over an order of magnitude. So yes, it is 20 dB per decade. The next thing we want to do is we want to locate what is our cutoff frequency. So our cutoff frequency is going to occur at the 3 dB down point, which is shown with this blue dashed line. So we can get an approximation of that. And I would approximate that as 3 dB down, so that's probably about 17 dB here. And so the cutoff then is occurring at 500. It's a little hard to extrapolate with the mouse. Also look up here in the passband region and we see that we have a gain of 20 dB. So the first thing you need to know is a gain of 20 dB does not mean a resistor ratio of 20. It means the log, it means 20 times the log of the resistor ratio. So in this case, that would mean a resistor ratio of 10. All right, so the first thing to do is to write a transfer function for that Bode plot. So we said our gain was 10, and we said our cutoff was 500, and it is a high-pass filter. So the transfer function would take this form. Now then we can go back to our equation that defined K and omega C in terms of R1, R2, and C. And so we can equate this back to that previous equation 2 slides back. So we find that 10 would be our R2 over R1 ratio, and 500 would be 1 over R1C. So we can, that's repeated right here. So in this particular problem, C was specified as 0.1 microfarad. So that then allows us to, as we said, you want to define R1 first so that you get the proper cutoff, and then you can set R2 so that the ratio gives you the appropriate gain. And so here would be the circuit that would then produce the plot shown in that Bode plot. So as we discussed in class, it is also possible to construct a Bode plot using to make a bandpass filter. So this is a Bode plot. The lower one is a Bode plot of a bandpass filter with a gain of 1 or 0 dB, and then the upper region is showing one with a gain of 20. It basically consists of a high pass filter that would have a cutoff frequency designed around omega C1, and a low pass filter that would have a cutoff frequency designed around omega C2. And then the gain is achieved by usually adding a third stage amplifier that basically just acts as strictly an amplifier. So this method of constructing a filter and its magnitude assumes that the lower cutoff frequency is significantly smaller than the cutoff frequency, than the upper cutoff frequency. And so the resulting filter is called a broadband bandpass filter because the band of frequencies passed is pretty wide. There is a definition there, and that is that the ratio of omega C2 over omega C1 has to be greater than or equal to 2. So let's go back to that previous figure. If omega C2 over omega C1 is not greater than or equal to 2, you can see what's going to happen. These two 3dB points, as this gets narrower and narrower, will close in on each other. And basically, you won't really have a region where this is flat. It'll just look more like a peak if these two get closer together. So it's no longer functioning as an efficient bandpass filter. So in that case, we would have to go with a different design referred to as a narrowband kind of filter. So the filters that we're talking about here, where you cascade a low pass and a high pass, that's a good design as long as you meet this particular specification on your bandwidth. Okay, here is an example of how that's actually constructed. We basically just cascade, which means connect in series, output to input, the low pass filter, the high pass filter, and then finally the inverting amplifier. So the low pass filter would basically meet the specification of the upper cutoff. The high pass filter will meet the specification of the lower cutoff, and the inverting amplifier meets the specification on the gain. So both of these filters are designed to have a gain of 1. That's for purposes of making the design simple and easy to both design and construct and model. So the transfer function basically then is the product of the low pass part, the high pass part, and the gain part, which would result in the line we see right here. And then if you multiply those out, you get the following transfer function. Okay, I want you to pay very close attention to this function right here. You notice that basically the denominator, if we were to work backwards, the denominator is factorable into a pole at the low pass cutoff and a pole at the high pass cutoff. So basically to work backwards, we would get this kind. Now let's compare that with this general form that we saw in chapter 14 when we discussed passive RLC filters. We said that the transfer function of a bandpass filter was the bandwidth times S over S squared plus the bandwidth plus omega naught squared. Let's go back to that previous, so keep this in your mind, and let's go back and look at that previous expression. And so you can see that because of the way the bandwidth, first of all, you can see that the numerator and denominator terms are not the same. So this is omega C2, this is omega C1 plus omega C2, so you don't have a beta up here. And then also, if you remember on our passive filters, omega naught was actually equal to the square root of omega C1 and omega C2. And that was then, so it's just a little bit different. The only way that these can be equivalent is if they can be approximated if the upper cutoff limit is much, much greater than the lower cutoff. So in other words, if it is very broadband, then what happens is if you take omega C1 plus omega C2, which was this middle term here in our transfer function that we obtained directly from the cascaded filters, if you take that, you can say that's approximately equal to omega C2. You would then get this expression, and that then would become equivalent to our general expression we got in chapter 14. But as a general rule, this is not the case. And so the transfer function for the bandpass filter for an active cascaded filter is different from the transfer function for the passive RLC. The final thing to look at is that it is possible to also make a band reject filter. In this case, rather than cascading a high pass and a low pass, we would put them into a summer. So we're summing the low pass part and the high pass part, which will give us the cutoff frequencies, passing the lower frequencies and passing the higher frequencies, and cutting off the frequencies in between.